So here we have a bulletin board. We have a teacher, Ms. Burke, and she's dividing her bulletin board into sections with ribbon. She's going to actually stretch the ribbon across from corner to corner. Okay, so what she's going to do, she has this bulletin board. She's going to stretch the ribbon this way. And then she's going to stretch from here to this way. Okay, so this is what it's going to look like. And we're going to figure out how much ribbon does she need. So let's start first. Anytime you're doing a problem with the Pythagorean theorem, you are going to be given the formula. You're given the formula in the formula section on the park, and it'll be on an anchor chart hanging when you take your exam, but it's not a bad idea to commit it to memory, and if you're working on something on paper, to write it down right away. What is the formula that we're going to use? Michael, what do you got?
A squared plus B squared equals C squared.
But A squared plus B squared equals C squared. And that means the square of the one leg plus the square of the other leg is going to equal the square of the hypotenuse. So in the rectangle, we already did the ribbons, but notice, what do we know about the ribbons? Yes, we're using the Pythagorean theorem, but it's a little bit more of a real-world problem. How am I going to find each of them? Think about that as we go through here. What is the length of this side of the triangle? Based on the information we're given, what's the length of A? 4.5. 4.5. Perfect. And what's the length of B? This is B right here. 6. So how could I find C? What could I set up? We have enough information. We know that A is 4.5 and B is 6. Do we have enough information to actually find the length of that ribbon? Why? Why do we have enough information right now?
Because the Pythagorean theorem states that if you have two sides of a triangle, that you could find the other side.
Exactly, and I'm going to add a little something to what you said. If you know the lengths of two sides of a right triangle, you can find the other one. For these problems, you're going to be given 2 of the 3 sides. Okay? Right now, what side are we finding? The hypotenuse. We're going to find that hypotenuse. What calculation would you put together? What are you about to type into your calculators to actually find this value? 6 times 6. And then what? Who wants to add on to what Tyrone said? Michael, what's the next part?
4.5 squared.
And that's going to give us what value? Don't give me the number. What would it be? Yeah.
It would be that the hypotenuse, so like I guess that's squared.
I'll use C just to show it, but that calculation that we're walking through right now is not actually the answer, right? It's going to represent C squared. Okay, so as we go on to the next slide, start to do that calculation on your calculator. So let's just recap what you just said. You said 6 times 6. If this here is 6, and this side is 4.5, this side, we don't know. So we did 6 times 6, and then we added that other side times itself. And what is 6 times 6?
36.
36. And what is 4.5 times itself?
20 and 1/4.
What is it?
20 over 1/4.
20 and 1/4?
20.
So 20.25?
Yeah.
If I add them together, what do I get?
56.2.
Good. So would it make sense that the length of that ribbon would be 56 inches? I'm sorry, feet, because that's 4.5 feet by 6 feet. No. What do I still need to do? I need to find the square root of 56.25. And what is the square root of 56.25?
1.870.
Hold on, what? I heard a few numbers.
7.5.
7.5. Say 7.5 or 9.
7.5. Yeah.
We could always always check that if you wanted. You could put 7.5 times 7.5 to see if it works. So now we say here that we have 6, we have 4.5, and we said based on our calculations that the hypotenuse is 7.5. So does that number make sense? We want to think about a couple of things. What do we know about the hypotenuse? There's 2 things we know for certain. One is that it's across from the right angle, which here represents that it is. What else do we know about the hypotenuse? It is the longest side. Does that make sense here? Is it the longest side?
Yeah.
Yeah, so we could say based on our calculations that that would be 7.5. So now you've done the Pythagorean theorem, you've done the calculation, but now we need to take it one step further and actually answer the question. When you see some of these real world examples, they may ask you for a little bit of an extension. So now, how much ribbon does she need? Think about it before you call it out. We found that the hypotenuse is 7.5. How many feet of ribbon does she need?
15.
Why 15?
7.5 for one and 7.5.
Yeah, there's actually 2 lines here that represent. This hypotenuse is for this triangle, right? We calculated at 7.5. But then if we did the same calculation for this hypotenuse using this triangle, notice that our side lengths are the same. So this would also be 7.5. Okay, so your answer here, like you just said, would be 15 feet, about 15 feet. So the Pythagorean theorem lets you find an unknown sine length. We have a squared plus b squared equals c squared, and we've been working with that formula for a couple of days now. But sometimes our answer doesn't end up being a crazy decimal, which we would refer to as an irrational number. Who remembers what it means to be irrational?
That it's never ends.
Never ends, and what else about the decimal? Because we have a decimal, I'll counter what you're saying. While it never ends, 0.33333333333 is not irrational. That actually is a rational number. It's 1/3. So it's not just that it never ends. What else? An irrational number never ends and never what? Think about pi. Never ends.
Never repeat.
And it never repeats. So a lot of times, based on what you've done for the last couple of days with Pythagorean theorem, you have seen irrational numbers as your answers. They're decimals that never end and never repeat. So it is helpful to recognize something called Pythagorean triples. And you're going to write these down in your notebook. These are Pythagorean triples. So you're going to write all 5. Okay? What this means is if I have a triangle with a side of 3 and a side of 4, the hypotenuse is 5. A side of 7 and a side of 24 would give me 25. A side of 5, a side of 12 is a side of 13. A, B, C. A, B, and C. And what we notice when we utilize these Pythagorean triples is that any whole number multiple of those side lengths is also a Pythagorean triple. For example, if I have a small triangle and its sides are 3, 4, and 5. 3 squared is 9. 4 squared is 16. Those together are 25, which equals the square root of 25 is 5. Okay? So that's not irrational. That hypotenuse is a whole number. Okay? Let's say I had another triangle, and this side was 6, and this side is 8. Without even doing the Pythagorean theorem, what's the hypotenuse of that? Don't call it out. Think about it first. If I have this same triangle, looks the same, but this one's just bigger. So instead of a side of 3 and a side of 4, this is a side of 6 and a side of 8. What must the hypotenuse here be? Why? Yeah, if I multiply 3 by 2, wrong way, I get 6, and 4 times 2 is 8, which means this would be 5 times 2, or 10. Now, if I needed to do the calculation to prove it, I could. 6 times 6 is 36. 8 times 8 is 64. Those two numbers together equal 100. The square root of that is 10. These are really helpful to have because you will see examples where the triangles are going to give you Pythagorean triples, where maybe one of the sides is 5 and the other side is 12. You may not, if you have these committed to memory, which some of them you might. 3, 4, and 5 tends to be the one that is easiest to remember. If you have these to memory, then you don't always have to go through a squared on your calculator and then add it to b squared on your calculator and then find that number and then find the square root. If you have some of these Pythagorean triples, and again, I would say the two that are probably the easiest to remember are these only because their numbers are a little bit smaller. The larger ones, even I have trouble keeping track of. But 3, 4, 5, or any multiple of that, they're all going to be Pythagorean triples. So make sure you have these 5 written down. Okay. These are examples where a squared plus b squared, if I found the square root of c, would give me a whole number, whether it's 5, 13, 17, 25, or 29. Those Pythagorean triples will not result in irrational numbers. Is anyone still writing this down? I'm sorry? Just that they're called Pythagorean triples. You don't necessarily need to have the definition, but what is helpful is to know that any multiple is also a Pythagorean triple. So the example that I drew, where you have the triangle of 3, 4, 5, would result in a triangle if I multiplied everything by 2 of 6, 8, 10. That idea might actually end up saving you a lot of time. If you're I-ready group 2, you can transition over now after you write these down. Is anyone still writing this or can I slide? So we're going to practice a little bit, just for a few minutes before we do a DOL. And let me pause here the recording.